junction is that when you are in the reverse mode, or even forward mode, you have this depletion region, right? This depletion region is interesting because you have, in the case of this junction diode, you have positive ions. You got negative ions on the P side and positive ions on the N side. So there is net charge distribution here, right? So it kind of looks like a capacitor, right? It has positive charge on one side and negative charge. But it's not exactly like a parallel plate capacitor if you look at it directly, because these charges cannot move. These are not free charge carriers. Nonetheless, I still think of it as a capacitor. Why? Because if you think about it carefully, it's an incremental capacitor. In other words, if I change the electric field across this thing a little bit, if I apply larger electric potential, what happens is that I change the number of positive and negative ions I have on the opposite side on the depletion region. So to do that, I have to provide net charge in and out of it. So as a black box, if you don't look at it inside, for changes in electric voltage, it behaves like a capacitor because I have to provide net current into and out of it. Right? And that's why we call it a capacitor. And in that sense, it's really the plates of this, where are the plates of this capacitor? Where is the change in the charge happening? It's here, at the edges of the depletion region. Right? So if this part of the depletion region is called XP, the length, and this the depletion region on the other side is Xn, what my total capacitance is per unit area, the capacitance per unit area of cross section of this thing is silicon, epsilon of the silicon, the permittivity of the silicon, divided by the spacing of these two equivalent parallel plates, Xn and Xp. Right? Does that make sense? So if I want to calculate the capacitance per unit area, that's what I need to calculate. The width of the depletion region, or XD. Is Xn plus Xp. So how can I do that? Well, I'm assuming it's an abrupt junction. And let's say, at that point, at some point, we are looking at the distribution of charge. So let's start with that. So I'm looking at rho of X, where X is the horizontal dimension. Okay. So when I have the depletion region, what can I say about the charges I have? I know on this side I have positive charge, and I know I have negative charge on this side, right? So what is the density of the charge density on the positive side, on this side? On the N side. What is the density with this rho? ND. ND. Why? Because these are just the ions, right? The dopants that are ionized. And we said they are all ionized. So it's ND here. And this is minus NA by the same argument. And if this is Xn and this is Xp, so this is positive charge, this is negative charge. What can I say about the areas of those two rectangles? Is there some sort of relationship that should hold between them? They should be equal, right? Why? Charge neutrality, conservation of charge. Total net charge has to be 0. Right? So that tells me that Xn times Nd is equal to Xp times Na. Okay? That's what it tells me. Okay, now if I have the charge density distribution, charge density at any point in space, I can use that to calculate what? My electric field. Right? So I can determine the electric field at any point as a function of x. So I'm interested now in E of x. Now the electric field is negative because it will be pointing to the left at all points, because I have positive charge on the right hand side and negative charge on the left hand side. So what is it? How does it behave? First of all, tell me how it looks like, the electric field. What is the electric field outside the depletion region? If my charge distribution looks like that? 0, right? So I start from 0, and then I have, at this point, something starts happening. And so how does it change? How does it behave? What will it look like? What kind of behavior do you expect? So if I go inside here, how do I calculate the electric field. If it's a uniform distribution of charge here and there. Basically electrostatic, right? Gauss's law, one way to calculate it. You have to make a Gaussian surface, and you can put one side of the surface on this side and one side on the other side, and all the flux will come out of here. Well, will be pointing in this direction. And that will be equal to the total net charge in here. Right? You have to integrate the total charge inside that space, and it would be basically xp times NA times x. So it would be linear. The other way to think about it is that you know that the electric field is the integral of the charge distribution of rho. Right? So, and by looking at that, you basically realize that if this is constant, this would be linear. Go like that. And it peaks here, obviously, because that's when you have most of the negative charge on one side and the positive charge on the other side. And it goes down to xn. So this is xp minus xp and xn. And this is Emax. Or let's say minus Emax. Okay? What is Emax? Let's calculate Emax using Gauss's law. You know, if you have a charge density, surface charge density sigma, and this sigma is different from that sigma. The electric field associated with that is sigma, like this, a sigma on the negative side on this one side and positive on the other side, sigma over epsilon, right? On the silicon. One way to think about it is that you have a surface charge density, and you can form a Gaussian surface here. And on this side, you know the electric field is 0. So on this side, the total electric field, E times A, has to be equal to the total charge inside this thing, which is sigma times A divided by epsilon. The A's cancel, and that's what you get from basic electrostatic. Okay. So that's what it is. So I need to calculate my surface charge density. Right? What is my surface charge density? If this is my volume charge density, Q and A is my volume charge density. So that it is that times xp. So it's going to be Q NA xp divided by epsilon something. Which is, incidentally, with that equation, equal to Q ND xn over 7. Epsilon 7. E is going to be Q NA xp divided by epsilon silicon, which is equal to Q ND xn divided by epsilon silicon. Okay? Does that make sense? Do you agree with everything I've said so far? If you have doubts about it, raise your hand, ask a question. Do you agree that it has to be linear? Do you agree that the maximum electric field is given by that? Do you agree that we have no electric field outside? Right? So that's the electric field distribution. Now, if I have the electric field, I can calculate the electric potential. How do I do that? Minus integral. You integrate it one more time with minus, right? So you integrate the electric to calculate the electric potential. What you do, you basically, it's an integral of that. So on this side, and therefore it becomes quadratic. Up to this point it's constant, so let's say, and then you go down, and then you come up to this point, and then it becomes flat. And let's associate different names for the potential drops on this side. On this side we have psi n, which is going to be the area of this triangle, right? Because it's integrated. Which is what? Which is xn E max divided by 2. And you got psi p on this side, which is xp E max divided by 2. Right? So that's it. And the total potential drop, of course, the delta or the total potential across the junction is the sum of these two. Okay, so let's calculate that. What is that? Before I do that, let me rewrite this E in a slightly different way. Because you look at each one of these expressions, it's defined in terms of one side of the junction. I prefer to define it in terms of xn plus xp, because that would be a good quantity. I basically try to calculate xn plus xp. Right? Let's state E in terms of xn plus xp. So how do I do that? Well, I noticed one thing. Let's go there and calculate xn plus xp from that. So if I use xn plus xp, and so I write it as xn plus xn times nd itself is going to be NA divided by NA plus ND times XN plus XP. Right? So I can take this, plug it back into this equation, and get Q ND NA divided by NA plus ND divided by epsilon silicon times XN plus XP. And you can see this is a more symmetrical way of writing the same thing. It's Emax. Right? Do you agree? It's symmetrical in terms of both sides of the junction. And now I plug that in here and calculate the total potential drop, which in general is what? Which is the built-in potential drop, psi naught, if we had, minus VD. The external potential drop across applied, right? Because that's what the effective potential barrier height would be. So for a negative voltage, VD, this increases the potential barrier height. Right? For a positive one, it decreases it. So that's the voltage drop across here, and that is the sum of these two. It's psi n plus psi p. By the way, it's actually psi, but it's kind of funny to say psi coincide. Proper pronunciation. Xn plus xp. So it's the sum of these two, and I get that term. And if I plug this from here, I will get Q over 2 epsilon silicon Na plus NaNd divided by Na plus Nd times Xn plus Xp squared. Right? So that's the total potential drop. But I know this. This is the parameter I apply. And this is something built in that I can calculate based on Na and Nd, the doping concentration. What I'm trying to calculate is this quantity. So I have to solve it for that, which I can do, and everything else is also on known quantities. So when I do that, I get XD, which is the depletion width, which is by definition Xn plus XP, XP is going to be psi naught minus VD times 1 over Na plus 1 over Nd from that, and then you get 2 epsilon silicon divided by Q, and then you get, and that's it, I think, square root of that. So that tells you something interesting. You remember I mentioned this earlier, that the width of the depletion region, in fact, grows only as square root of the potential applied, electric potential. So you double the electric potential, the width of the depletion region only goes at square root of 2. And that should not be that surprising, because look at that picture. In this kind of junction, if I double the width of the depletion region, think about this. If I double the width of the depletion region, it would be here. Right? What have I done to the area under this triangle, which is this basic potential difference? The area under this triangle is the sum of these two. If I double the width of the depletion region, I have quadrupled the area of the triangle. And in other words, I've quadrupled the potential drop. So for a doubling of potential drop, I have to only increase the width of the depletion by square root of 2. Okay, so that's one thing I can learn. Because these equations by themselves are useless. I mean, not useless. I mean, they're not necessarily that meaningful unless you understand what's the meaning behind the equation. They're not that useful. So that's one thing that it tells you, is square root dependence. The other interesting thing that it tells you is that the width of the depletion region is dominated by which side? The lightly doped side or the highly doped side? So let's say one of the NAs, let's say one of them, for the sake of argument, let's say NA is much greater than ND. So you have a lot higher doping on the P side than the N side. Which side will carry most of the depletion width? Which side is the side that most of the depletion region falls into?
Lightly doped side.
The lightly doped side, right? Because the smaller one of these two, because they are in the denominator, will give you a larger term in the summation. And it also makes sense. sum of the charges to be 0, that has to compensate the charge on the other side. So it has to extend over a large distance. Right? So it's interesting. It's the lightly doped side that determines the width of the depletion region and hence the capacitance. Because the next step is just to plug that into the first equation we had and calculate the capacitance per unit area. And that basically, there's an epsilon there and it's epsilon, so it gives you, yes, Q epsilon silicon over 2. And then gives you 1 over NA plus 1 over NB 1. And then you have all of that square root, and then you have in the denominator sine naught minus BD square root of that 2, which I can rewrite as, I can absorb all of this, I can factor all of this rest of the parameters out, so I can get Q epsilon silicon over 2 sine naught divided by 1 plus NA plus 1 ND. And then 1 over 1 minus VD over sine naught. And I can say, well, this is really nothing but the junction capacitance when VD is 0. When I have no external potential, right? When I apply no external potential, VD is 0. This term is 0, so this whole thing is 1. So this is basically what I call the CJ0. The junction capacitance at 0 external potential. So I can rewrite this as CJ naught. It's basically another way of defining CJ naught. 1 minus VD over sine naught. Half. Okay? Now, that tells you something interesting. That this is, first of all, this is a nonlinear capacitor in the sense that it's a voltage-dependent capacitor. So the capacitance depends on the voltage. Now, it could be a good thing or a bad thing depending on what you're trying to do. If you're trying to make a varactor, the capacitance that you can control with the voltage is a good thing. That's one way of making it. You can use it in reverse bias diode as a varactor. If you're trying to get a very nice capacitance, fixed linear capacitance, not to introduce harmonic distortion or things of that sort, then this is a bad thing. So, it's a blessing or a curse, depending on how you look at it. Now, the interesting thing is that this capacitance, though, again, is dominated by the lightly doped side. Now, but what happens if I increase the doping level on both sides? Let's say, well, yeah, it's dominated by the lightly doped side, but if I go to higher doping levels, would it increase or decrease the capacitance? Think physically. Increase it, right? Physically, what happens if I increase the doping level up there? If the doping level goes up, what happens to the width of the depletion region? Goes down. So the two plates of the capacitance are brought closer and closer to each other. The capacitance goes up. Yeah. Right? Okay. That's one thing. And of course you have the epsilon of silicon and the charge of electrons, so these are also there. As you expect. So this is interesting because you have this capacitor, but now this behavior, this square root dependence, where did that come from? This square root came from the fact that I had an electric field or electric potential drop that was proportional to the square of the depletion width, right? Now, but that happens to be a special case when your junction is an abrupt junction. You basically have uniform distribution of dopants on both sides. You have uniform distribution of NA and uniform distribution of ND. And that's not, this exponent is not generally 1/4. So let me show you another example. Let's do it kind of qualitatively and see if it makes sense. So now instead of an abrupt junction, let's assume I have a linearly graded junction. In other words, the doping concentration grows in a linear fashion. So at the junction point, it's 0. But if you look at the doping concentration, you have basically on this side, it's NA and ND. So NA grows like that, and ND grows like that with the same slope. Right? Now, if I have something like this, let's see what happens. So let's look at the picture. In terms of charge distribution, raw, of course, in this case, they would be all, if they have the same slope, xn and xp will happen at the same point, but it doesn't matter. So I will have a certain amount of positive charge that's balanced by the negative charge on the other side, right? It's linear. So like that's the charge distribution. That's how it works. Okay? How about the electric field? What would be the electric field behavior? Now, if this is linear, the electric field is the integral of the charge distribution, right? So it has to be quadratic. So this becomes quadratic electric field. Now, if it's quadratic, what can I say about my potential, electric potential drop? It's going to be cubic. Right? So my psi naught minus Vd will be proportional to xt cubed. And therefore, when I calculate my xt, it will be proportional to psi naught minus Vd, the third root, the cubic root of psi naught minus Vd, right? And therefore, when I go through this calculation again, here, instead of this exponent, 1/half, I will get 1/3. So my capacitance in this case then would be Cj naught divided by 1 minus Vd over psi naught 1/3. And in fact, you can control this exponent by engineering the doping profile of the junction. In one of the homework problems, you will do a different kind. I'll give you what kind of, well, you calculate what kind of exponent you need, and then from that determine what kind of doping profile. Right? Any questions about that? Alright, no questions? So we looked at the PN junction, right? So far we looked at it forward bias, we saw that what happens to the current, and we looked at it in reverse bias and we calculated the capacitance. This capacitance, by the way, is quite important. We encounter it a lot in devices that we have. Any kind of transistors or diodes and all those things in electronic design. So when you get to the design, it's important to understand what this capacitor is and where it comes from. Okay, now there's one more thing about this junction diode. Let's look at the distribution of the current. Let's go back to forward bias mode and look at the distribution of current and see what we can learn from that. So one more time. Let's say this is our junction. This is the junction. This is the depletion region. So P-type, N-type. And then let's say I have applied a forward bias to this thing. So there's current flowing here. Now, let's look at different components of this current. Because you know that we have holes and electrons on both sides. And we want to see what happens. So we saw when we apply forward bias to this junction, what we are doing, we are lowering the potential barrier. The height of the potential area is lowered, so more electrons can go. So in this case, at this point, what do I have? I have a certain number of electrons, let's say a certain level here, that can cross. Now, when they go through the junction, they basically cross the junction, and they end up on the other side. But now, this is an electron in a p-type region. Now, it's a minority carrier. So its probability of recombination is much higher. So what happens is that as it goes, you can look at the distribution of its electrons, and they gradually dissipate, basically. They exponentially, you can actually solve it numerically, analytically, using differential equations. It becomes a first order differential equation, it's a diffusion. And what happens is that you can see that the component of the current carried by the electrons on this side start dropping. Because the farther you go, there's a higher chance that more of these electrons recombine with the holes that you have plenty of here. And they basically recombine. And from that point on, the current will be carried by the holes. Because for every hole lost, you have to put another hole in, which corresponds to current. That current flowing in. Now, how about holes? Let's say you inject holes. Now, holes are also injected from this side to that side, right? Holes are going through as well. Now, so you have a certain number of holes at any point in time. So let's say there's a certain level of holes injected here. And they also go through an exponential drop. gradually disappear. So now, what can you say? So this is JP on this side. Again, there are minorities. What can I say about the electronic current on this side and the whole current on that side? Can you tell me something about the electronic current on this side? How would it look like? What percentage of the current is carried by electrons on this side? Okay, let me show it to you and see. Can you tell me if it makes sense? Shouldn't it be the complement of this? Because for every hole lost, if you have lost an electron too, it has to be compensated. So the less of the current that's carried by holes, the more of it is carried by electrons. Because the net current has to be constant. And the same thing on the other side. So you can say on this side also you have something like that for JP. And this is JN. And therefore, the total net current, which is the sum of these two, is constant. If this thing has a constant cross-section, it has to be, right? It's kind of like a slab, rectangular design, has to be constant. So this is J total. So that's the way the current is distributed. But why is that important? Well, think about this. You know, so far I've created this device that has this IV characteristic that looks like this. It's got exponential behavior. So if I look at ID versus VD, it is an exponential like that. Okay, more or less. Now, but this is not very, I mean, it's useful for certain things. If you want to make a rectifier, for instance, you can make it and all sorts of things. But it's not a very good amplifier. I mean, how can you make an amplifier with two terminals, first of all? It's kind of tough, right? I mean, you need, ideally, what you need is a control terminal that's separate from the output terminal, right? And you, of course, need the potentials to be referenced to some common terminal at least. So you need at least 3 terminals. Okay. So with 2 terminals, it's hard to make something like this. But now, the question is there something I can do about these guys? Is there something I can make? Well, one of the things I could think about is making a 3-terminal device, a PNP or NPN junction. So I add a third one, and the objective here would be, in this picture, the problem here is that I'm losing my minority carriers by the end of this process. I'm losing most of them. Now, what if I have another piece of semiconductor somewhere close that can capture most of these before they are completely lost? And the way to capture these minority carriers would be to capture them into a region where they are not minority carriers anymore. Right? So for instance, if I want to capture these holes injected from this side, I need to have another P region close enough before they are all recombined with the ends. So that's the basic idea behind the bipolar junction transistor, or BJT. So let's see if we can start taking the BJT. So here we have 3 different regions. So let's look at an NPN. So we have an N region, we have a P region, and we have another N region. And we would like to make this P region large or small. If you want to capture, you want to be able to recover as many of the minority carriers injected from one side to the other before they are lost. You want to make it as small as possible, as thin as possible. So we have something like this. And then we want to create a situation where we inject charge carriers into this. So we apply a positive potential here, this side. So they have this diode, we have 2 diodes here, right? We have 4 bias, VB. So let's call this terminal, by the way, emitter, for the reasons we'll see in a second. And this is called the base. And then we would like to be able to collect them somewhere else, right? And to be able to collect them, what's the best way? If I can create an electric field that absorbs these charges, so the charges injected from this side to that side are called what? What kind of charge carriers are injected from this region to that region? Electrons, right? So I want to capture electrons. So I need a field that allows me to capture these electrons. Which way would that field point? The left or the right? To absorb them into this third region. To the left, right? Because the electrons are negatively charged, so I have to absorb them here. And for that to happen, I have to get this junk to second junction reverse bias. So if you look at the depletion regions, there is a depletion region here, and there's another depletion region here. I have these three regions. But let's see how it works. Now, let's look at the energy band diagram for this. I have two back-to-back diodes initially, it appears like. But I have this one forward bias, so I have a lower potential barrier here. Or let's say, let's not apply voltage to that first. Let's look at it as a unbiased. So this is the way it looks like initially. Okay? So these potential barriers are high enough, so very few electrons can cross. So I have the distribution here and only a few of them can cross that are compensated by the ones that are thermally generated from this side, and the same thing from the other side. Okay? But now I'm applying a positive potential across here. And what that does, it lowers the potential barrier height. Right? So I'm lowering the potential barrier height here. Here. And I'm applying a negative potential, negative charge on the negative voltage drop on the other side, so I'm increasing the potential barrier height. Now, what happens? Now I have a whole lot of new electrons that can cross. Like dots, like it's a p-n junction dot. So these guys can cross, who couldn't before. And they go here, and they're randomly moving, right, thermally. So there's a finite probability for them to get to the other side. Now, once they get to the edge of here, the electric field will suck them in and throw them inside the collector, where they are again majority carriers, because it's an n-type region. So they are minority carrier for a very short period of time for this in this region. And the shorter you make it, the fewer of them you lose. But what I've done here is interesting, because I can control the number of electrons that cross by controlling this potential. Right? What it really controls is the current through this terminal. So by controlling the voltage across, let's say this is the common terminal, right? By controlling the voltage applied to this terminal, I can control the current through a third terminal. And that allows you to make a lot of interesting things. Okay? So that's the thing. But now if I ask you the question of what is the distribution, what is the, and for obvious reasons, as you can see in this mode of operation, this is where you emit electrons, where you generate charge carriers. In an NPN transistor case, you have electrons emitted out of here. So that's the emitter. This is called a base for historical reasons, because initially they made them in a different way. I'll tell you later how they made the point contact transistors. And this is where they are collected. So that's the collector. So this is the emitter, base, and the collector of the transistor. Okay. Now, and you can of course make it, so this is an NPN, and you can make it PNP. PNP. And the notation for this, of course, symbol for NPN is like this, and the PNP is like this. The one with the arrow is the emitter, and the way to think about it, of course, is that the arrow is one diode here, and so there's the p-n junction diode is pointing, and this diode is pointing this way. Okay, now the question is, what is the current? Can we calculate this current? The collector current for this transistor, the simplistic model. In terms of the base emitter voltage. Well, let's calculate this electronic current. What is the size of this electronic current? We have already done this, right? This is the diode, the same thing as the diode, p-n junction diode. So I know this current is, the collector current is going to be the same thing if none of them are lost, at least in principle, ideally. My collector current would be simply, again, an IS, which may be, well, it's a different IS for every device, obviously. E to the KT, which is about 20, KT over Q is about, at room temperature is about 26 millivolts. Right? So when we apply much higher voltage than that, this current becomes substantially greater than that. So this is a good approximation, simply IS E to QVBE over KT. It's actually, it's an approximation, the whole thing is an approximation, but this is the expression we'll use for the forward. And you can see that now at this time it's current of a third terminal that's controlled by that voltage. So what it allows me to do is to, by applying small voltage to the VBE, to the base emitter junction, and control the current and let that current pass through a resistor or some other kind of load and make an amplifier in the simplest form. Okay, now, so let's do this. Now, the way I've shown it, I've ignored a lot of the other things that can happen. So let's look at them a little more. Look at this device a little bit more carefully. Now, first of all, the way I describe it to you, I made it sound very simple. I said, well, okay, yeah, I lower the potential, all these electrons go through here, so I have a lot of current flow. But unfortunately, I have a problem. What is my problem? Not all of my current is carried by electrons. I also have a second component of the current in this junction. And what is that? Holes, right? I also have a distribution of holes here. And what I've done, I've also lowered the potential barrier for the holes. So now a whole lot of holes can go this way. But unfortunately, these holes are not going to do anything useful for me. But they are not collected, unlike the electrons, they're not collected on the other side. They go and recombine in this region. Right? And that process is an inefficient process. So I can define an efficiency for this process, which is called the emitter injection efficiency. So let's see. So how would you define the emitter injection efficiency? I want to define an efficiency that the closer it is to 1, the better off I am in that sense. So the useful component of the current is the electronic current. And the useless part of it is the whole current. So if I look at the total current, the ratio of the electronic current, the total current, I can define this quantity called emitter injection efficiency, which is, we show gamma. By definition, it is what? It is the ratio of the electrons injected from the emitter into the base to the total number of the ratio of the current carried by the electrons plus the current carried by the holes. Okay. Right? And this is the emitter injection efficiency by definition. So I want it to be as close as possible to 1, right? I want it to be 1. I don't want this to be large. I want most of my current to be carried by the electrons because those are the ones that I can collect. How will I do that? How can I do this? How can I say again?
Different doping concentration.
Sure, yeah. The one way is to start with a much larger electron concentration to begin with. Right? If I have a lot more electrons on this side and much fewer holes on the other side, yeah, sure, I lower the potential barrier and more of these holes go through, but there are a lot fewer holes on this side that want to go this way than electrons that want to go that way. So most of my current will be carried by that. So I want this side to be much more highly than the base. And actually, I usually try to dope it as high as I can. And sometimes we show it at N+. So the emitter side has the doping concentration that's higher than the base side to get as high an emitter injection efficiency as possible. Now, there's a second efficiency component to this, right? Which is the transport efficiency. And it comes from the fact that not all the electrons that are injected into the emitter make it to the collector. Right? Some of them recombine here. Okay? And this recombination process also results in some loss of electrons. So of base transport factor shown with alpha t, which is the ratio of the electrons that make it to the collector to the electrons that are ejected into from the emitter. And you want this to be as large, as close to 1 as possible. How would you make this as close to 1 as possible? Make the base very thin. Also reduce the possibility of recombination. So you have to remove things from the base that can result in more recombination. For instance, if you have other kind of impurities, they are called trap. They can create trap energy levels, and they increase the chance of recombination. So now the total ratio of the collector current to the base current, to the emitter current, right, will be, in this case, if these are the only two parameter things limiting my efficiency, it's going to be the product of the two efficiency processes, right? And this is by definition called alpha, the alpha of the transistor, which is less than 1. The collector current will be smaller than the emitter current. And how much smaller is determined by these efficiencies. The closer they are to 1, the better off I am. Now, let's look at something interesting. So let's see what happens. I have one more thing. I know one more thing. So this is the emitter current. This is IE. This is the collector current. Well, no, I'm sorry, the other way. IE, IC, and then there's IB, the base current going in. What can I say about these three currents? I still have KCL, right? Kirchhoff's current law. I have conservation of charge. So IC plus IE has to be equal to IE. Okay. But I can write my IE as IC divided by alpha, based on this expression. And therefore, I can write my IB as IC times 1 over alpha minus 1, which is IC 1 times 1 minus alpha over alpha. In other words, IC is alpha over 1 minus alpha IB. And now this quantity is defined as beta of the transistor. Now, I want alpha to be as close to 1 as possible, right? So in a properly designed transistor, alpha is close to 1. And therefore, beta could be a large quantity. Now, but you can also see it's extremely sensitive to the parameters of the transistor, right? So just to show you how it works. So if my alpha is 0.9, what's my beta? This is 0.1, this is 0.9, so it's 9. If it's 0.99, it would be 99. And if it's 0.999, it becomes 999. So basically approximately 10, 100, 1000. So you can see a small change in the efficiency results in a much larger change in beta. And that's why beta is such a sensitive parameter, and we'll see later on, you don't want to design circuits that rely on the value of beta in their operation. So you want to make it as independent from beta as you can, because otherwise you will depend on something that changes if you breathe on it. Literally, you breathe on it, it changes. Okay, now, and these are of course DC quantities, so sometimes we show this as beta DC and alpha DC, low frequency. And we'll see what happens when we change the value. Now, I think I'd like to stop here because the next thing I'm going to talk about is quite important. I'm going to spend a fair amount of time on it. We'll do that next time. But so that's for that. But we have time for a few more questions if you have questions about it so far. That's what we've done. So what we'll do next time is the following. We'll take this and we look at the flow of the current and where each one of the components of the current go. Then we'll try to derive a model for this transistor. We'll derive the ever-small model, which is a nonlinear large signal model. And then we'll go and use that to derive the small signal model. And then we'll look at the parameters of the transistor, the other parameters, like the capacitance, and other behavioral trends. We'll look at some of the second order challenges and effects in the transistor. And we'll continue from that point on. And then we'll, I guess not next time, probably right after that, we'll talk about MOSFETs at some point. But we'll understand the bipolars first and look at the curves and what they mean and different effects in the transistor. We'll look at the phase modulation and early effect and things of that sort, and what controls different parameters of the transistor. But BJTs, and then we'll talk about MOSFETs, and we'll continue our discussion, and then we'll get into circuits. All right? Any questions? Everyone is on the mailing list, right? I mean, the sign-up sheet that we had last time. We haven't sent an email yet, but because we are going to announce the TAs and their hours and all those things pretty soon. If you're not on the list, make sure you come by and add your name to the list, and then we'll take it from there. Well, have a good week.